we ran, right? So some of you saw this slide just the other day from the other course. And if you aren't taking 1090 from me, then you should really pay attention and ask questions, all right? So the way I think about this is you read it from left to right, and when it says exists, then I have to come up with an object, right? How do I prove that an algorithm exists? Is I design an algorithm for the problem. And then once I have the algorithm, then how do we prove the for all is we let it be a worst case input from the adversary, right? And so this is what we've been doing all along, right? How do we say that P is computable? Why is sorting computable? Because there is an algorithm, insertion sort, that on every input gives you the right answer, right? And people see here P is the problem sorting. So P of I is saying what the required output is. It's the sorted list. And A is an algorithm, say insertion sort. And what do you want? You want it to give the correct answer, right? So do people kind of understand this a bit, right? And so how does the game work? Hey, I'm claiming I have an algorithm that solves the problem. The adversary comes, studies your algorithm, right? Sees how you're moving the keys into the cells, designs the key to get them all to collide, right? And that's not very nice, right? All right, so here we're going to add in some extra time. We also want the time to be fast. Right, okay. All right, so now we're going to do the same except this randomized thing, right? And so I'm going to cut. What we're going to do is, well, you don't might. We didn't cover quicksort. You might not, don't remember quicksort because you might not remember it. Or you may or may not know quicksort. You know quicksort? Random pivot, did we do it? All right. All right, so right, what's the key here is that I have an algorithm that works, right? And the adversary knows the algorithm, but doesn't know the coin flips, right? So it knows that if it comes up heads, it's going to use this hash function, and if it comes up tails, it's going to use this hash function. But the adversary doesn't know the random coins, right? And it has to come up with an input. And then we flip the random coins, and then we check to see if it works, right? And right, I guess this is saying for every input, we never want this thing to make mistakes, right? So for every input, we want it to make the right answer, but we're going to have that the running time depends on the coin flips, right? And then we can talk about the expected running time over the coin flips, right? Everybody kind of understand the game? Right, so for every input, you have right, no matter what this is saying, for every input, there's no bad input, because for every input over the randomization, the expected is good, right? So it's kind of like we really get to choose the hash function after the adversary is given the input. All right? So they're worst case coin flips, but not worst case inputs. So there's another way of looking at it where you can also add in here, well, you might not get the right answer, right? But the probability of the wrong answer is really small. We're not going to be doing that. All right. So if we're playing this game here, we have this algorithm, and then the adversary comes up with some input, and then we flip coins, right? And one way to do that is for every possible key in the universe, we're going to flip enough coins to put it into a random place in the array, right? If we're going to use lots and lots of randomness, then we could do that, right? Does that make sense? So this is completely chosen randomly. Every key, independently at random, we decide where it's going to go, right? And then it doesn't matter what the input was, right? It's really, we're throwing each ball into a random bin, and we can talk about how many collisions we expect to happen, right? Does that make sense? Yeah. So this is, when you're actually coding it up, you flip the coins ahead of time. But our assumption is that the adversary is not told what the coin flips are, right? They're kind of hidden in the box. All right, so they go somewhere around. And so it's like throwing balls into bins, which, what do you need to know about that is, if you look at a particular ball is going to share its bin with how many other balls? Half of the balls are going to be alone, right? But maybe it collides with a couple other things, but it's going to be a constant, right? But it's not so good. There are a couple bins, constant number of bins that are going to have a log-in number of balls. So this is something that's useful in computer science, all right? So it's going to be, these are the integers, right? And these are the integers mod 5. And what do they contain? They contain 0, 1, 2, 3, 4, these 5 numbers, right? And how do you multiply? Well, A times B, you take A is something from this universe, B is something from this universe, you multiply them, and then you take the mod P being 5, and you get something from this universe, right? Does that make sense? I mean, that's how we do math. And you might say, why do we do it mod P, right? So here's just an example. 3 times 2 equals 6, which equals 1, right? And so actually, I did this randomly, but it gave me exactly what I wanted, right? What does 1/3 equal? Can we divide, right? In integers, you can't divide, right? But here I can divide. Anybody want to guess what 1/3 is? What's the definition of 1/3? A number that I multiply by 3 and I get 1, right? Can you give me a number that I multiply by 3 and I get 1? It's right there, guys. What is it? 2. It's 2. 1 divided by 3 equals 2, right? And you might say, that's weird. And I'd say, yeah, but it's cool. And so in the integers mod of prime, you can always do that. Now, if we did mod 6, life's not so good, because 2 times 3 now equals 0, and that causes you problems, right? But if it's mod of prime, that's never going to happen, right? So we work over integers mod of prime so that you can always divide, right? So that's what we're doing in here, right? Did we lose her? Right. So what we're going to do is we choose some prime p, and we're going to work over the integers mod p. So p is a prime, it could be 5. And so we're going to choose a to be in this range, right? We choose a random a, and then you take the key times a, mod p. So we're working all in the mod p world. Why are we doing that? So we can divide and we can do math, right? And then just to get it in the right range, we do mod n, right? And then what are our values? Well, our universe is going to be huge, right? And our n is going to be relatively small because you're actually storing the numbers. And then what p, well, it's just going to be as big as your universe, but that's not really a problem because, I mean, suppose, right? I mean, let's look at social insurance numbers. Then the size of u equals 10 to the 9, right, which is big. Can I have an array this big? No. But can I have a p this big? Yeah, it's just a 9-digit number, right? I just need p. This is a 9-digit prime, right? And I can get 9-digit primes easy, right? Does that make sense? So that's what we're doing here, is we're choosing some quite big prime number, bigger than our universe. We're choosing a random value in the, I'm going to call it a field. Why? Because I can divide. Integers you can't divide, and fields you can divide. That's just math talk, right? Everybody see that? People understand what we're doing? Maybe not why, right? So there's not a lot of coin flips here. I'm just choosing one A, right? It's some randomness, but it's not a lot of randomness, right? And the integers mod p, they form a field, which are similar to the reals because you can divide, right? And integers, and then you taking it mod capital N brings it into the array, right? Does that make sense? And then we can say, what probabilities do we have? We don't have total independence anymore, right? What does independence mean? If I tell you something about, if I flipped all independent coins, then if I tell you, for example, hey, you did really well in your bowling the last 3 times, how are you going to do in the next time? Well, if each bowl is independent of the random, then your next bowl has nothing to do with what happened in the past, right? But if we don't have purely independent coins, then if I tell you what happened in the past, it can give me information about what's going to happen in the future, right? So there's not complete independence, right? And so we want to see how much independence do we have? And we have what we call pairwise independence. And what does that mean is if I took any key whatsoever and I asked, what's the probability that that key gets mapped to a particular square in the array, the probability is going to be 1 over n, right? Why? Because you have n squares, and we're putting it into a random one, right? But now what we're saying, suppose I go ahead and I tell you that key 1 goes into cell 5. Now, you give me any other key, where it goes is still random, right? Everybody kind of get that? If I tell you where one key goes, where the next key goes is still random, right? So, no, actually, I actually lied to you there. If I tell you where key 1 goes, then it tells you information about key 2. But if I just ask, do these two keys go to the same place? Do they collide? For every two, if you wanted them to, right? I mean, let's not get into it. It's just saying, for any two keys, the probability they collide is still small, right? And everybody get that? Why is it 1 over n? Because if I threw the first key somewhere and then I threw the second key somewhere, they're in cells in my array. And if I put it in a random cell in the array, the probability it goes where key 1 is 1 over n, right? We could fix it to say what I said, but I got rid of the plus b. Often the hash key is a times the key plus b, where b is also random. But I felt there was no need for that. It just wasn't helping us, right? That would have given us more randomness. But here, all we care for for every pair of keys, the probability they collide is small. Now, if I give you 3 keys, now there may be some intermixing about whether they all land in the same place or not. Yeah? Yeah. Yeah. Yeah, exactly. Exactly. And so, me being a math geek, when I made these slides, I proved all of this. And why is it in a small font? Because I knew I wasn't going to cover it. All right? But if you want to know the proof, there it is. All right. So, here we're inserting a key, and the expected number of keys that it's going to collide with, right, is you work it out. I mean, again, we don't need all the math, but one thing that's true about sums, I don't know if you've done this over randomness. If you have a sum of a number of random variables, then the sum of the expectation is the expectation of the sum. It's very powerful, right? So we're using that here, and it turns out that the probability of colliding is if we're inserting right? Suppose you insert capital N key, little n keys into an array of size capital N, right? And I'm inserting somebody new. Well, what's the worst case? The little n haven't, right? So here we have our big array, size capital N. And I put little n in already. And suppose they haven't collided yet. Now I take a new guy and I put him in a random place. What's the probability he collides with one of these? Right? Well, it's going to be n over capital N. Right? And that would be true if we put it in purely randomly. But we're not. We're putting it in by just choosing this A. And that still gives us what we want here. Right? Because you have this pairwise independence. People kind of getting it? Right? The study of randomness is very subtle, but you should have some flavor of it. Any questions about it? And you know there's not going to be a question like this that Jackie approves of, right? But I still think somewhere in your head you should know how these things, kind of things work. Not just because of hashing, but randomness in general comes up, right? Right, so this is just saying you don't get more independence, right? Because we only chose one number, there's not more independence than that, and that's okay. All right, so this is where I said people often do, they choose a random A and a random B. But what does B do? B just moves you around the array. That doesn't help with collisions. So I'm like, why do we put a B in there? It doesn't do us any good whatsoever, right?